Wow. You people are in for a treat with this one, I think. I hope you are watching this video on a Monday fun day, or Friday fun day, or Tuesday fun day, or Sunday fun day, some sort of fun day, because this is a treat, I think anyway. I sure do wish we were together in class doing this together. I wish that I could see what I think would be the pleased looks on your faces. I don't like that I'm doing this all by myself in my office, in my pathetic little social distance stance here, but desperate times call for desperate measures and all that sort of thing. But wow, what a fun ride we have today. The point of this video is to actually now show you a complete example of the SIR modeling process. We're going to build the model, solve it, interpret the results, recalibrate against the data, and just see if the model did what we wanted it to do, if the predictions made sense. What fun that is. Okay, so the complete modeling process here. The example we're going to use is a strain of the flu from the late 1960s in New York City. At the time, it was called the Hong Kong flu, and that is what it's still referred to as in the literature. At the time, no flu vaccine was available, no flu shot back then. So many more people died than would have died today. Many more people were infected also than would have been infected today. I'm starting with this example, this old example, this sort of, you might think, obsolete example, because the data is so clean and so known. Okay, this outbreak of the flu is extremely well understood. So we're starting with like the most well understood example that we can. We will turn to COVID-19 later, I should say, but we're not going to attempt to model that on our first stab here because there's so much that's unknown with the COVID-19 outbreak, right? The data is a mess, and there's very little that's known about it relative to old strains of the flu. But anyway, we'll talk about COVID-19 later. So here is the data from the Hong Kong flu in New York City in 1968 through 69. This is the death data. So at the time, there's not really any data available for the number of cases. So recall with the SIR model, there's no variable for number of dead people. The number of dead people is incorporated into the recovered variable. But what we're ultimately after, what we ultimately care about in these models is the number of sick people at a given time. And that's not what this is. However, if you are going to die from the flu, you can reasonably assume that these people got the flu about a week before. So we have data suggesting that on average, if you're going to die from the flu, it takes about a week from infection for that to happen. So this data is kind of a image of the number of sick people over time. It's just shifted back a week. So notice the rise and fall here, right? Week 1, we have 14 deaths all the way up to 190 here. That's the peak, and then it tapers off by week 13. So the death data peaks in week 6. Therefore, we can reasonably assume that the actual number of sick people, the epidemic itself, peaked in week 5. So when we build our model, we can see if this sort of thing happens over time, a peak in week 5 and this number of deaths. So here's the SIR model from the last video. I'm not going to read all this to you. It's just from the last video. However, notice that if we want to actually get a model for this disease, for this strain of the flu in New York City in 1960s, we need to know 4 things. We need to know the B value for that strain of flu. We need to know the K value for that strain of flu. We need to know the initial percentage of susceptible people, the initial percentage of infected people. There was no flu shot, so we can reasonably assume 0% of the population was recovered. We can reasonably assume nobody was immune. So to set up a model to solve, to make predictions about the strain of flu, we have to find those 4 parameters. We have to estimate them somehow. Well, K, recall, is just the length of an infection in an individual, just how long are you sick on average. The flu is very well understood. For this particular strain, you're sick for about 3 days. It wasn't a particularly long disease. We'll assume for now that each sick person has a potentially infecting contact every 2 days. So once every 2 days, an infected person has a contact sufficient to spread the disease. The flu is not super contagious relative to other diseases like coronaviruses, like SARS or like COVID-19. So this is a kind of a relatively low B value. For this particular virus, as I said, nobody was immune. We'll assume that there were 10 people infected initially. You could assume any small amount you want, and it's not really going to change the behavior of the model in any significant way. So you could put a 1 right here if you wanted to. Just have one person, flying in to infect the city, whatever. So recall the capital letters are the raw totals. So if there are 10 people initially infected, and the population of New York City was 7.9 million at the time, here's the number of susceptible people, and nobody is recovered. And then here are the corresponding percentages. So I of 0 is approximately 0. It's very small, right? Initially, there's a very small percentage of people infected, and the percentage of people susceptible is basically 100%. So with all that said, here's the model. Here is the model with the numbers filled in, the constants filled in. So this is the model that we need to solve. We need to figure out what S is, what I is, and what R is. So before I show you how to do that, let me just first ask you, as if we were in class. I'm pretending we're in class to make myself less depressed. So pretend we're in class, and I ask you, this is a system of differential equations, right? There are 3 equations, 3 unknowns. The 3 unknowns are S, I, and R. If I relabel those variables as like x1, x2, x3, like x1 prime, x2 prime, x3 prime, it sure seems like we're in chapter 7, right? Because chapter 7 was about systems of differential equations. We spent most of our time on 2x2 systems, but we saw some 3x3 systems and talked about how to solve them. So if we're going to solve this model, can we use the tools of chapter 7 to solve this? So you may want to think about that. You may want to pause the video and think about that. But assuming you now want an answer, the answer is no. You unfortunately cannot use chapter 7 to analyze this because notice there's like an x1 times x2 right there. x1 times x2 right there. Chapter 7 was about linear systems. And in linear systems, you can't multiply the variables like that. They have to be separated by pluses or minuses, and they can be scaled by constants. But that's it. So this intermingling of variables here means the system is not linear. So what that means is that chapter 7 can't help us here, at least not directly anyway. So we're going to solve this model in a second, but it's worth pointing out we can't solve it chapter 7 style. So when I say we are going to solve the system, what I actually mean is that we're going to let a computer solve it, but the computer is going to use Euler's method, which you guys understand. So in principle, you guys could do this by hand. It would just take a long time. We're going to let a computer do it to save us time. So I'm going to show you how to do that in a second. Also worth sort of banking here for future reference. The death rate was pretty low, 17 per 100,000. We'll need that when we're checking the data we have against the model solutions we're going to build here. Okay, so let me show you how to use Python to solve this system. And again, also I should say, right, when I say solve, I mean get graphs of the 3 functions. We're not going for formulas for the solutions. Euler's method builds you graphs. So that's what we're going to do. So to have Python solve this for you, you have to open Anaconda Navigator, the software I asked you to install. And I believe I mentioned in an email or something, just sometime previous to this, that I spent much time looking for an online Python compiler that could draw these graphs for us, because I didn't want to bother you with downloading software. But I spent hours looking for this, and I couldn't find one that worked. So I apologize for you having to download this. Once this comes up, there are 7 different sub-applications that you could launch, little launch buttons here. You want to launch Jupyter Lab, so click right here. What will eventually pop up after it thinks about it for a minute or so is a Python compiler that opens in a web browser. So notice it opened a Safari window for me. Okay, so what is open here, what's on my screen, probably looks nothing like what's on your screen. The reason is because I have all sorts of pre-existing work I've done in this. So all this stuff here should not be on your screen, and all this stuff over here should not be on your screen. These are pre-existing projects I've worked on that I've titled terribly, as you can tell here, right? So I don't know what's in any of these until I open them. But whatever. So you should see something like, actually, this. Over here, you should see blankness, basically. There should be nothing here. So with that open, let me now scurry over to Moodle. So on the Moodle page, if you go to the Epidemic Models Materials section, you should see a couple of different text files. One is called SIR code percentages. One is called SIR code raw numbers. So the model I showed you on that slide was phrased in terms of percentages. You could, of course, build the SIR model in terms of just the raw numbers, the capital S, capital I, capital R, and then get graphs for those curves if you want to. It's just up to you. So I'm going to grab the percentage code first, just because that's what the model on the slide was. Okay, so I'm going to select all this. I'm going to copy it. So I've copied all this. Now I go back to my Jupyter Lab window, wherever that is, right here. I click here in this little panel right here and see how the cursor is blinking at you. That means you can now put code in here. Paste your code in here. Okay, so a lot of this, right, looks completely mysterious. Most of you don't know any Python at all, right? So, of course, if you look at this and it looks confusing, it's perfectly fine. Scroll up to the top, though. Almost all this code you're not going to mess with, and you don't need to understand how it's working and what it's doing. All you need to notice is that there are the parameters of the model input here. And this little blue text here with a hashtag in front of it tells you what things are. So this capital N is the total population, which I've already preset to 7.9 million for you, but in a different problem, you may change that number. I naught, comma R naught are given by these two numbers. So the initial number of infected people, notice the capital I here, right? The initial number of infected people you put here. The initial number of recovered people you put there. And so notice those also match already the model from the slide. So we don't need to mess with that. Now, next, we have to input B and K. We have to tell the program what those two parameters are. So B, we said, was 1/2, so I'll put a half there. And K was 3, we said, so I'm going to put a 3 right there. Okay, so far there are only 5 things you might mess with, right? The total population, I naught, R naught, B and K. The last thing you'll want to mess with is, notice here, you can control basically how far into the future you want to look. So when you build these graphs, you can tell Python like, hey, I want a graph from day 0 to day 30, or from day 0 to day 50, or whatever. It depends on how long you think the epidemic will last, you know. But you can look, like, say, 700 days into the future if you want to look 2 years into the future. This epidemic, we think, tapered off after 13 or 14 weeks or something, right? That first slide suggested. So I'm going to put 100 there. That seems to be the time scale of this particular epidemic. Once you type that stuff in there, you don't need to mess with anything else. Before I run the code, though, let me just point out real quick. If I scroll down a little bit, notice nowhere in the code does it say the phrase Euler's method. However, that is what this code is doing. This ODE int command right here, it's not worth worrying about what's actually happening here in terms of Python, but what's happening in terms of math, that command invokes Euler's method. It hands the differential equations off to an Euler's method script or something, and then it builds the graphs for you. Okay, so once you've entered the numbers you want, number of days, B and K, whatever, you click play. And sometimes you have to click it twice for reasons I don't quite understand, so I'll click it again. Whoop, sorry, your cursor has to be in this window somewhere. So make sure your cursor is in this window when you click play. So click play, and then out comes a graph. Look at that. Isn't that nice? It just graphs the percentage functions for you. So little s, little I, little r as functions of time. So the blue curve is the susceptible curve. So initially, notice it starts at 1 because 100% of the population is susceptible. And then over time it falls, right? That's all it can do because we don't create new susceptibles. As people become sick, this curve falls. The red curve, I, is the infected curve. So it looks like nobody really even starts getting sick until day 55 or something, right? And then it peaks at day 78 or something and then tapers off. This green curve is the recovered curve, right? The percentage of people who are recovered over time. So this tells us actually everything we want to know on some level about this epidemic. We know there was an outbreak. We can see it peaking here, right? We also, by the way, know the percentage of people who got sick. How many people in New York City got sick? Well, recall that in this model, the only way you become recovered is by being sick in the first place. So initially, nobody is recovered, right? But then over time, notice this green curve levels off around 0.6. So roughly 60% of the population becomes recovered. And where those people come from, by the way, notice the blue curve starts at 100%, right? 100% of people are susceptible at first, and that falls to around 40%, right? So both those things combined tell you the same thing, that 60% of the population got sick. So that's the first thing you should take away from this graph, is that 60% of those roughly 8 million people will get the flu, we think. Just real quick, if I ask you how many people got sick or what percentage of people got sick, a common wrong answer is to look at this I curve and notice it peaks. I mean, it's hard to tell from the vertical scale, right? Notice the peak, though. It peaks at a height of like 5%, or maybe 8% or something. I don't know, right? So a common wrong answer is to say 8% or 5% of the population becomes sick. That's wrong, though, because this peak, that's just saying that on a particular day, 5% of the population was sick, day 78 or something, right? Over time, though, this 5% here, they get well somewhere in here, right? And there were people who were sick before them. So in total, 60% of people got sick. So you don't want to just look at this peak. You're actually integrating under the curve here. The area here will give you that 60% number. So anyway, the peak only tells you how bad it got on a particular day. That's how you solve these models. Boom. It's just this picture here. And by the way, I also wrote this code so that if you look over here on the left, it's a mess for me because I got a ton of stuff. You should see something called sir.png. You can download that if you want to. If you right click and then do download. So you can't just put this picture on your computer if you want to. So that's kind of nice because you can like zoom in on it. Or I can make it bigger. Anyway, so that's how Python solves these things for us. Just does Euler's method. All right, so let's go back to the slides and think about how well our model did, okay? So according to our model, 60% of the population or so becomes sick. The death rate is 17 per 100,000. So how many people die do we predict? Well, 60% of 7.9 million, that's how many people get sick. And of those, 17 over 100,000 die, right? This is like the death rate here. So you're just doing the death rate times the number of people that get sick. And you get 806 people. If you go back to that slide with the death data and add up all the deaths, the actual number was 1,035. So it's not like that far off, I guess, but the error is 22%. That's bad. That's a really bad error. Okay. Furthermore, did our model correctly predict the timing of the epidemic? And the answer is like, no, it's terrible. Our model showed the epidemic starting at day 55. Again, let me just bring up that picture. Right, this I curve doesn't start building, doesn't start actually going up until like day 55 or so. And that's terrible, you know? Our data showed the death peaking in week 6, which was what, like 42 to 49 days in? So the timing is like way off. So this model we built, turns out, wasn't very good, you know? I mean, it at least had an I curve that looks like an I curve, like it goes up and then goes back down. But it failed to accurately predict the number of deaths. It also failed to predict the timing. So what do you do with that? Well, what do you do is you say, well, in this model, this K value was measured empirically, right? That 3-day thing, we just know that. We also are, you know, you can always assume a small initial amount of infected people. It's not like, you know, whatever, 200,000 people with the flu just suddenly show up in your city, right? So I of 0 is basically fine, and S of 0 is basically fine because it's just, you know, it's just, if there's a minuscule amount of infected people, then everybody's susceptible, you know. So what that means is that our B value is probably off. Okay, so we recognize that, and we say, fine. So our B value is off. This B being low, right, the lower B is, the sort of better the epidemic is for society, sort of like the farther into the future that peak goes. If you make B higher, you'll get that peak higher, and you'll get the epidemic shorter because the disease becomes more contagious. So more contagious means like a worse outbreak. Okay, so let me just show you that. Come back here. What if I make B 0.65? So here in the code, here's where B and K are. I'm going to put a 0.65 right there. And then I'm just going to, again, run. Okay, here's the picture now. Check that out, right? Now this peak is at day 41 or something, I don't know, right? And now, let's see, how many people get sick? Well, we fall from 100% susceptible to about 20% susceptible, maybe a little more, right? So it looks like maybe 80%-ish of the population gets sick, maybe 75%-ish gets sick now, and the epidemic peaks at day 41. Let's think about that. Okay, so in my slides here, it looks like I took the 75% becoming sick number, right? So if you, again, you do 75% of 8 million or so, right, and then times the death rate gives you 1,007. Oh, and that's like basically what the death was, right? And furthermore, the timing is way better, right? The timing actually sort of agrees with the what we said initially, right? We initially said that the epidemic should peak between days 42 and 49, I believe. Anyway, so that's how the SIR modeling process works. That's pretty fun. Real quick, I just want to show you the other code you could do, this raw numbers code. Let me just show you what that does for this. So again, you select it all, copy it, go back to Jupyter Lab. All this code here, just clear it out. So I'm going to select it and then copy over it, or sorry, paste over it the code I just had. So just put this other code in there. Again, you got to set the parameters. So N was 7.9 million, so on. I not, R not okay. Let's think about our initial B value, and our initial K value was like this, right? And I'll, again, set the number of days to 100. Now if I run this, there's the same picture, just with, see the raw number of people, right? So the recovered people build up to about 5 million, right? So roughly 5 million people get sick or so. Susceptibles fall from 8 million to, again, it's hard to eyeball this sort of thing. Susceptible people fall from 8 million to a little more than 3 million or something. Anyway, so you can also just get raw numbers like that if you want to. Okay, so back here, let me quickly finish off now. So again, at this point, I would look at your faces and hope to see just pleasure on your faces, right? That's so nice that you can do this, you know. Conclusion of this, right? To model future outbreaks of Hong Kong flu, we have an estimated B value now of something like 0.65. So we would use that to estimate, you know, like once this spreads to Kansas City, we would use that B value to estimate that outbreak. And then we could, again, after the fact, check that B value against the Kansas City data and see how that went, you know. Finally, just to conclude here, it is worth pointing out that I've been using this phrase epidemic, this term epidemic, without defining it for you. The epidemiological literature defines it like this. What does it mean to have an epidemic? If your I curve ever has a peak, that's what it means to have an epidemic. So if you were asked in your homework or something, right, does an epidemic occur here? If your I curve would ever have a peak, the answer is yes. Otherwise, the answer is no. So what would it mean not to have a peak? Let me just come back here. Okay, so I still have the raw numbers code in there, that's fine. Let me set the B value to something smaller, like not 0.5, but like 0.35 or something, and run that. Let's see what that does. Now you see no peak, right? The infected curve is just flat. So basically, what we're learning here is that with a B value that small, the disease is not contagious enough for an epidemic to occur. So you can sort of play around with these values and see sort of where that threshold is. So 0.35 is low enough, there's no epidemic, but remember 0.5 was high enough, there was an epidemic. So you can start playing around with these values, like at 0.42. With 0.42, notice the S curve is going to tick down a little bit, which means this I curve actually will build to a peak if you give it enough time. So let me give it enough time. So 300 days now. Yeah, you still get a peak with that, right? But 0.42 is sort of on the boundary of having an epidemic, right? Because you just barely see that uptick. So anyway, you can just play around with it. And it's fun to play around with to get these little pictures, right? Yeah, so again, with 0.39, there is barely a little uptick here, you know, just barely. Okay, so hopefully that was interesting for you. Your homework basically just you take this code, you take the code, you plug in the values. Like where? Let me just get to a model. Where is it? Okay, so you plug in these values for a given model, so the context changes depending on which homework problem you're doing. Plug in the values, have the code spit out the graphs for you, and interpret the graphs just like we did here.